Hi, my name is Renan Shekel. I'm a student in Yaron Brondar's Complex Photonics Lab in the Hebrew University of Jerusalem, and I will speak to you today about shaping entangled photons through multimode fibers using mechanical perturbation. Well, first one might ask, why should we send photons through multimode fibers? So some motivation comes from the field of high-dimensional quantum key distribution, QKD. While usually people use these Q bits, which live in a two-dimensional space, to encode the information in QKD, it is possible to encode the information in a higher dimensional space, allowing more information per photon, which allows to create a higher capacity channels. In addition, it has been shown that protocols using higher dimensions are more resilient to noise. Specifically, it is convenient to encode the information in the spatial degree of freedom due to the fact that it's relatively easy to encode information using spatial light modulators. So when performing the QKD through a fiber, so of course one can't use a single mode fiber because it supports only a single spatial mode, and one must use a multimode fiber. However, also in regular QKD in free space, it is still can be useful to use a multimode fiber for the collection. This is because it is relatively hard to couple the light efficiently into a single mode fiber, especially when coming from very far, like from a satellite, because the single mode fiber has a small core and also relatively no numerical aperture. So using a multimode fiber can help to enhance the coupling efficiency. Well, if multimode fibers are really so great, so why don't you use them all the time? So some of the problem comes from the fact that when light, even classical light, propagates through a multimode fiber, it is scrambled. So if one focuses a laser into a multimode fiber, so usually a few of the spatial modes will be excited, and even if only one of them is excited, so there might be some mode mixing, which will excite multiple modes, and their interference between these modes will create this grainy speckle pattern. So to overcome this, people use spatial light modulators, where they somehow study the exact scrambling happening inside the multimode fiber, and then use SLM to overcome this scrambling. In fact, people in these works below have used multimode fibers together with SLMs to create quantum circuits, where they begin with some biphoton state, and they create the SLM and the multimode fiber. They use them in order to create these general transformations to the biphoton state. Note, however, that the actual shaping is happening outside the fiber in the SLM. So in this work, what we do, so we shape the photons propagating through the multimode fiber while inside the fiber itself. So how do we do this? So we begin with an entangled photon source where we use SPDC, spontaneous parametric down conversion, where a pump beam hits a nonlinear crystal, creating these pairs of entangled photons. Then we send it through a beam splitter, where probabilistically one of the photons goes to a heralding single photon detector, and the other photon goes through the multimode fiber. At the other side, we have another single photon detector, which scans the spatial plane, the transverse plane of the fiber, and the coincidence counts between these two detectors will give us the spatial distribution of the heralded single photon. As discussed, this distribution will be a speckle pattern. However, it turns out that the case is actually worse, and this speckle pattern is highly dependent on the geometry of the fiber. So having smaller perturbations on the fiber, only something that you touch it a little bit, and it will change the speckle pattern. So what we do is we turn this nuisance into a feature, and we have these control perturbations along the fiber, and we use a feedback loop with signal from the detector in order to find perturbations that will be good for our cost function, such as localizing the distribution of the single photon to a single spot. So we do this using what we call the fiber piano. So we have these piezoelectric actuators, a few tens of them going along a multimode fiber. And each actuator can go up and down, creating these three-point contacts with the fiber, which induces bends on the fiber. And we use some optimization algorithm, namely PSO, particle form optimization, in order to search for a good configuration of perturbations, which will, for instance, localize the distribution of the single photon to a single spot. So let's see some results. So we'll actually show this in two modalities. The first one is what we talked till now, where we have the beam splitter before the multimode fiber, and only one photon propagates through the multimode fiber. So as we said, we begin with a speckle pattern, and after doing our optimization protocol, we end up with really a nice focus spot. If we want to quantify this, so we define the enhancement as the ratio between the peak to the background of multiple random configurations, and we see an enhancement of over an order of magnitude, which makes us very happy. However, if you think about it, this configuration is relevant for settings such as communications, where Alice has these entangled photons, and she keeps one of them by her, and she sends the other one to Bob. However, in the context of these quantum circuits, so they have a biphoton state, and they want to act in it with some general transformation. Now, of course, the more general transformation includes both photons. So in that case, in that context, it makes more sense to send both photons through the multimode fiber. So both of them go through the multimode fiber, and then also the static and also the scanning detector are both on the other side of the fiber. So we begin again with measuring this two-photon speckle, and after doing our protocol with the actuators, so we get this nice focused spot in the correlations between the photons. To show a slightly larger degree of control, we then perform again the same sort of optimization, but this time our cost function, instead of being localizing to a single spot, so we try to localize to two spots in both the one photon and two photon configurations. The last result I want to show you has to do with coupling light from a multimode fiber into a single mode fiber. So going back to free space QKD, so the collection of the light is usually done using single mode fibers. Single mode fibers are really great because they have very good components and infrastructure, they have a good interface with the detectors, and they have low dispersion and low polarization mixing. However, it is really hard to couple into them efficiently. So a possible solution for this is to couple the light into a multimode fiber, and then use the fiber piano to couple the light from the multimode fiber into a single mode fiber. Actually, using the multimode fiber as some sort of funnel. So we do this, and we show an enhancement of, again, of over an order of magnitude. I wanted to stress the point that that this sort of thing is relevant also for regular two-dimensional qubits, where you can code the information in the time bin or in polarization, because here the multimode fiber really only helps in the collection to couple efficiently into the detectors. So looking forward, one of the main advantages of our approach is that it is all fiber. This allows us to have a low footprint on the collection telescope, and it can also be cheaper. A second thing with all fiber is that there have been recent works showing that they can create entangled photons inside the multimode fiber. So if you create them inside the fiber and then you shape them inside the fiber, so it can be really useful to create these quantum circuits, and also for entanglement distribution when everything happens inside the fiber. There's also a second, more fundamental theoretical advantage of our approach, where in the traditional methods using SLMs, so what the SLM does, it shapes the light at the input of the fiber. Now with this all linear, we consider it linear, so you can think of the light at the input and the output of the fiber as vectors, and the transmission through the fiber can be modeled through a transmission matrix. And what traditional methods do is they shape the vector at the input of the fiber. However, in our approach, what we do is actually we change the transmission matrix of the multimode fiber. So instead of acting on the n degrees of freedom for n mode fiber, we actually have n squared degrees of freedom, allowing us theoretically to create these general transformations with a much larger degree of control, which isn't possible using the traditional methods with SLMs. So if you want to hear more about this, or you're welcome to read the paper we very recently uploaded to the archive. And for a more general review of the field, so you can read this perspective from Nature Physics, which we published in our group, Nature Physics, just about a year ago. And with that, I will thank you for your attention. I will be very happy to hear your comments and your questions. Thank you very much.